Hi, and welcome to Module 5 of Lecture 10. In this module, we're going to discuss some basic operations to do with matrices. Now, in the previous module, we introduced the matrix, discussed some types of matrices and where they're used. Here, we're going to focus on the nuts and bolts of manipulating matrices. Here, we'll do the most straightforward operations: addition, subtraction, multiplication. In the next module, we'll deal with some newer operations like the trace and the determinant. Okay. So let's start here. In some ways, the most basic operation is one you haven't seen before, but it's pretty straightforward, so it's included here, and it's called the transpose, the matrix transpose. Okay. The transpose of a matrix is the matrix sort of flipped around its axis. So, axis I say in quotes here. So let's see how that works. If you have a matrix, a square matrix, 2, 3, 1, 4, the transpose of this matrix is a matrix that's flipped around the diagonal. So the transpose, represented by oftentimes a T, a capital T, is going to be 2, 1, 3, 4. So for this little 2 by 2 case, you just kind of flip the thing below the diagonal with the thing above the diagonal. We can do more complicated examples. First, the square matrix. Let's see, 2, 3, 1, 4, 5, 6. I should have done this whole time. It's much easier. Transpose. Now for this one, diagonal stays the same. But now all the things below flip with those above. So the 3 and the 4 swap places. The 1 and the 7 swap places. And the 8 and the 6 swap places. So again, the transpose is just flipping it around the diagonal. And we'll give the formal definition in a second. Note that we can actually define a new kind of matrix this way that we didn't talk about last time, a symmetric matrix. A symmetric matrix had the same elements below and above the diagonal, such that if you take a transpose of it, you get the same matrix back again. So a symmetric matrix has A transpose equal A. And you can draw it like this. So for instance, if this were 2, 5, 9 again, and 3, 1, 3, and 3, 1, 3, then the transpose is the exact same thing back again. The 3 and the 3 change places, the 1 and the 1 change places, still a 5, 9, and the 3 and the 3 again change places, and it's the same matrix back again. So we can define another kind of matrix, a symmetric matrix, when the transpose of the matrix equals itself. This covers a lot of cases you'll deal with in practice, but transposes are more general than just applying to square matrices. You can take a transpose of any matrix, or a vector for that matter. If you had a column vector, 1, 3, 5, the transpose of the column vector, that's a 5 down here, is equal to the row vector, 1, 3, 5. Or, a little more generally, if you had a 2 by 3 matrix, so let's do 1, 3, 5, 2, 4, 6 down here. There's my 2 by 3 matrix. The transpose is going to be a 3 by 2 matrix. So you're going to have 2 columns and 3 rows. So the rows and the columns flip. And this actually gives you the definition of a transpose. If you have A transpose, it's the matrix obtained by, so A transpose Ij is equal to Aj. So you take all the elements in the jth row and the ith column and put them for the transpose in the ith row and the jth column. Basically, you switch rows and columns. You can see how this works by looking at these examples here. So for this one, 3 is the first row, second column. So it must end up in the second row, first column, which it does. Similarly, this down here is the second row, third column. So it should be the third row, second column. Which it is. So everything's okay. So this, if this notation isn't great, you can define B equals A transpose. Maybe that's clearer than Bij, the elements of B are equal to Aji. Means the same thing. Sometimes you also often see transposes with primes instead of t's. This is usually clear because this A is a matrix, so the prime doesn't mean derivative, it means transpose. I'm going to stick to using transpose with a T because it's just clearer to me. It doesn't get people confused with derivatives. But that's it. That's a transpose. That's the very first of the matrix manipulations we're going to deal with. The next one is matrix addition. Matrix addition works the exact same way as vector addition. That is, if you have a matrix with the same number of rows and columns, or rather two matrices like that, you can add them together or subtract them from each other. So for instance, we'll start with the square one, and there's B. Well, what's A plus B? Just like for a vector, you add all the matching components, add all the matching elements together. So, and I should say, components is used often for vectors only, whereas elements is used for both vectors and matrices. You often don't say components of a matrix. Anyway, so you add this together. So 2 plus 5 is 7. I don't know why I made this so big. 3 plus 1 is 4. 1 plus 6 is 7. And 4 plus 0 is 4. That was an accident. And you get this singular matrix for A plus B. A minus B, same way. 2 minus 5 is negative 3. 3 minus 1 is 2. 1 minus 6 is negative 5. And 4 minus 0 is 4. So again, you just keep track of where all the elements are, and you can add and subtract matrices just fine. You can do non-square ones if you'd like to. So if this is, and B is 1, 0, 1, 0, 1, 0, just because it's easier, then A plus B is going to be 3, so it's 2 plus 1. Then 1 plus 0 is 1, and 3 plus 1 is 4. And 6 plus 0 is 6, and 5 plus 1 is 6, and 4 plus 0 is 4. So again, just keep track of the relevant rows and columns, and make sure you're adding the corresponding elements in the first matrix and the second matrix, or subtracting them. You can write this generally. So if A plus B equals C, then Cij, that's the ith element, ith row, jth column of C, and that element is equal to Aij plus Bij. So you just add the resulting rows and columns. And the same thing for subtraction. If A minus B equals C, then Cij equals Aij minus Bij. And you can't tell, but these are capitals and these are lowercase. So that's it. So addition and subtraction work just the same way you've seen before in vectors. You must make sure that the dimensions in both rows and columns of the matrix are the same when you're adding and subtracting, but assuming they are, you just add and subtract the elements directly, and there's nothing else going on there. So that's addition and subtraction. Now we go to multiplication, and again, there are two types of multiplication. Actually, there's more than two, but there's a type between a scalar and a matrix. Turns out that works exactly the same way multiplying a scalar times a vector does, maybe not surprisingly. So how do we do that? Well, if C is a scalar and A is a matrix, and C equals 2 and A equals, I'll start with the square one again, that doesn't make a difference at all. Then CA equals 2 times 3 is 6, 2 times 1 is 2, 2 times 5 is 10, and 2 times 6 is 12. And that's it. So when I multiplied, I do a scalar multiple of C. It doesn't matter if the number is negative or if A is square. So now if C equals negative 3 and A equals, let's do a different one this time, 3, 0, 1, 6, 2, 7. Well, again, then CA, multiply negative 3 times all the elements and leave them in the places they were before. So that's negative 3 times 3 is negative 9. Negative 3 times 0 is 0. Negative 3 times 1 is negative 3. Negative 3 times 6 is negative 18. Negative 3 times 2 is negative 6. And negative 3 times 7 is negative 21. Okay, that's it. So that gives you scalar multiplication. And if you want to do the general form, CA, if that equals B, then the ij element in B, the thing in the ith row and the jth column, is equal to the constant C times Aij, the thing in the ith row and the jth column of A. So again, Nothing different from vectors in the slightest. There's another dimension of the matrix of the vector, rather, another element to deal with, but it's the same exact logic, the same rules. Nothing has changed in the slightest. Okay, so that covers the straightforward stuff. Now, multiplication. Now, if you recall, we had a whole module about vector multiplication focused on, we looked at the dot product primarily, and we mentioned there are other kinds of multiplication out there, like the cross product and so on. Well, there are also multiple kinds of matrix multiplication. They also have different names. One dominates for all the stuff we're going to do, and that one is we just call plain matrix multiplication. And that often is a little tricky at first, but once you get the hang of it, it'll be pretty intuitive. So here we go. Let's say when I multiply the matrices A times B to get C. How do we do that? Now, before I go through and give you the examples, let's do the general case first. The formula for the ijth element of the matrix C is equal to the sum on K of aik bk j. And that is the formula for each individual element of the matrix C. Clearly that's a little harder than just adding things that are the same, and clearly we have different things being multiplied. So what does this mean? Well, let's think about what this k is. K for A tells you the column number, right? So when k is 1, it's the first column. When k is 2, it's the second column, and so on. B, the k tells you the row number. So it's the first row, the second row, and so on. So this is telling you is go through and first, and it's going to be equal. So it's A11. So for C11, you have A11, B11, plus A12, B21. Let's say it's a 3 by 3 matrix. Then you would have A13, B31. If there are 3 columns in the first in A and 3 rows in B. So this would be what you would get for C11. Now what does this look like? Well, actually, this is a dot product. And you can kind of see the similarity because you're basically multiplying 2 things together and adding them. But what are you multiplying? Well, all these things are the first row of A. So you're taking the first row of A and you're multiplying it by the first column of B. You're taking a dot product between the first row of A and the first column of B. And that's the first element. And that, as far as I'm concerned, is by far the most intuitive way of looking at the multiplication because it leads naturally to a nice, easy way of looking at matrices and knowing how to multiply them. So let's do that. I'll do examples first. So if this is A, let's see, let's do a nice 2 by 2. And this is B. What's A times B? Well, this says the first element of A times B is going to be the first row of A dotted with the first column of B. So one way to think about this is take the first row of A and the first column of B, and kind of in your head, take that first row, rotate it over, and dot it with the second one. So in your head, take the 2 and the 1 and shift it over here to 2 and 1 and dot that with 6, 2. Well, what's that? Well, a dot product takes each individual corresponding element, multiplies them together, and then adds all those products. So this is going to be 6 times 2 is 12, plus 1 times 2 is 2, or 14. So the first element is going to be 14. And that's how it works. So you got the first row, you kind of rotate it in your head, and dot it with the first column. Now what about the element over here? In this spot over here? Well, how would we do that? From the formula, we want to know the first row and the second column. Well, how would this formula up there change? Well, what would C12 be? Well, we'd have A11 as before, but now it'd be B12. And we'd have A12 as before, but now it'd be B22. And now we'd have A13 as before, but now it'd be B32. So all would change the very last column, the last index in the V's. What's that? Well, that is the second column of B. So to do the first row, second column element, you take that first row of A and you rotate it over and you dot it with the second column of B. So now we get 2, 1 dotted with 1, 3. Then we have 2 plus 1, 2 times 1 is 1. 1 times 3 is 3. That equals 5. So this has to be 5. Now what if we want to do the second row, first column? Well, again, it's the same exact logic, and I ran out of space, but the same exact logic. C21, you know what, I'm going to write it over here. I'll change it in blue. C21 would be A21. All the A's become 2's, and all the B's here become 1's. And that would be C21. Switch that around. So again, you take, I'll change the color over here, make green this time. You take the second row of the first column, of the first matrix, and you rotate it around and dot it with the first column. I'm not going to write this out now because I ran out of room, but 3 times 6 is 18. 2 times 5 is 10. 18 plus 10 is 28. So this number here is 28. And finally, the second row, second column element is going to be what you get when you have the second row of A dotted with the second column of B. So it's 3, 5 dotted with 1, 3. 3 times 1 is 3. 5 times 3 is 15. 3 plus 15 is 18. And that is our C. So, I really want to erase it right now because I want to keep working on this example. But there you go. That is how to multiply matrices. So a couple of things we should note here about this. One, this method works in general. Sorry, 1A, whatever. This method works in general. You can take the first row of the first row of the first matrix, kind of rotate it along, and dot it with the first column, then the first row and the second column, and so on, all across the number of columns the second one has, and that populates the number of columns of the multiplied matrix. Then you do the next row, so on and so forth. The number of rows of A will populate the rows of the multiplied matrix, which immediately tells you a couple of things. Which itself tells you things. First, the number of columns of the product will be the exact same as the number of columns of the second matrix. Right? You can see that several ways. One, every time I take the row on the left and multiply it by the thing on the right, and I just realized this looks backwards to all of you. I apologize. This way and this way. Every time I take this and multiply it, so on, going forward, right, that creates a new column of the new multiplied matrix, of the product matrix. So the number of columns in the second matrix is the same as the number of columns in the product matrix. You can also see that by looking way up here at the main equation. For every j, for every row, for every column of the second matrix, there will be one column of the product matrix. Now, for each row of the first matrix, you create a new row of the second matrix. Same thing is true the second row. For each row of the second, so for the second row, you create another row of the matrix. I can go off the camera now. You create another row of the matrix. and so on. So the number of rows of the product matrix is the same as the number of rows of the first matrix you're multiplying. You see it also up here. The I here stays around. So for each row of the first matrix, you have another row of the product matrix. So the rows of the first matrix and the columns of the second matrix determine the dimension of the overall matrix, and you can write that out. So if A is n by m, and B is m by, what should I pick, L, then C is m by L, then C is an n by L matrix. Now this immediately illustrates the second point, which is these m's must be the same. You cannot dot two vectors if they have different lengths. Therefore, the length of the row vector in the first matrix must be the length of the column vector in the second matrix. I think it's backwards or not. Anyway, so the length of the row vector in the first matrix must be the same as the length of the column vector in the second matrix, which means the number of columns in the first matrix, which is the length of that row vector, right? So one column, two columns, and so on, three columns, must be the same as the length of the column vector in the second matrix, which is the same as the number of rows in that matrix, and so on. So the number of columns in the first matrix must equal the number of columns in the the number of columns in the first matrix must equal the number of rows in the second matrix in order to multiply two matrices. If they're not equal, you cannot multiply two matrices. It's impossible. Okay, so there's that. So there you go. That is matrix multiplication, and that's the main thing you note here. Second thing which is not as obvious from looking at this, from looking at the equation, not that this was obvious, but this can be derived from the equation, a little more complicated, is that matrix multiplication does not commute. Now let's see if I can remember these matrices enough to actually replicate them. Let's see, 2, 1, 5, 3, 7. You know what? 2, 1, 3, 5, and 6, 1, 2, 3. 2, 1, 3, 5, and 6, 1, 2, 3. 2, 1, 3, 5, 6, 1, 2, 3. See if I can do that again. I should have written it backwards. Hoping that's correct, we could flip it around and multiply b times a. Okay. I'll do this one again because I screwed up and didn't do the right actual, because I remembered incorrectly. I'll do this one again really fast. So that's 14, and 2 plus 3 is 5, and so far so good. And 18 plus 10 is 28, and 3 plus 15 is 18. Hey, I did it right. I remembered. Okay. Here's you can remember only 7 numbers at once. Okay. So there's that multiplying. Let's do the same thing for this one. It's good practice. So first, we'll multiply 1 times 1. We'll dot these two vectors. So 6 times 2 is 12. 1 times 3 is 3. So 12 plus 3 is 15. And already, we have different numbers from before, right? It's not 14, it's 15. Now I can do the second one. So the first row times the second column. So that's 6 times 1 is 1. 1 times 5 is, 6 times 1 is 6. 1 times 5 is 5. 6 plus 5 is 11. Again, different. Now I can do next one. Now we'll go to the rows. That's all the columns we have because we've used every single column in the second matrix. Now we'll go in the second row to populate the second row over here. Well, 2 times 2 is 4. 3 times 3 is 9. So 4 plus 9 is 13. And finally, in the last part, 2 times 1 is 2, and 3 times 5 is 15. So this is 17. 15 plus 2 is 17. And that was the second row in the second column. So you see, multiplying them in different orders gives you different outcomes. Matrix multiplication does not commute. A times B is not the same in general as B times A. There are some examples which it is true. So A times I equals I times A, where I is the identity matrix. You can commute with identity. As you see later, A inverse in general equals A inverse A, because they both equal I. But in general, you cannot just commute these things in general. You cannot commute matrices AB does not equal BA. So that's the second thing to notice about matrices. They don't commute. So that's important to know. So we actually can refer to things as left multiplying by A over here and right multiplying by A over here. And these are not necessarily the same thing. If I have some matrix A, here I'm left multiplying by B, and here I'm right multiplying by B, and these can be different things in general. Okay. So we'll do one more example to show you how different size matrices work. Let's do this one. So 3, 1, 2, 1, 2, 3. 3, 1, 2, 1, 1, 1. Yeah, whatever. Okay. So now these are different size matrices. One is a 2 by 3 matrix, and the second is a 3 by 2 matrix. Now we can't add these, we can't subtract these because they have different dimensions. But we note that this first matrix is 2 by 3, and the second matrix is 3 by 2, so we can multiply them because they have the same interior. The number of columns of the first one is the same as the number of rows of the second one, so we can multiply them. And we should get a matrix that is 2 by 2. And that can be helpful. And in fact, we're going to do an example just like this at the end of this lecture when we talk about OLS and using these kind of matrices for matrix multiplication, multiplying matrices of data to get the coefficient beta. We'll give an example just like that. And that's a common way you see matrix multiplication is when you're doing OLS. The second way we said before was when you are repeatedly operating on some state vector with a transition matrix. Okay, so how do we do this? The exact same way. So first row dotted with the first column. 3 times 3 is 9, 1 times 2 is 2, 2 times 1 is 2, so it's 9 plus 2 plus 2 is 17. No, it's 13. Sorry, 13. Doing well right now. Second one, first row times second column. So here everything's multiplied by 1, so it's 3 times 1 plus 1 times 1 plus 2 times 1 is 3 plus 1 plus 2 is 6. Now we do, where'd that go? This one. Second row times first column is 1 times 3 plus 2 times 2 plus 3 times 1 is 3 plus 4 plus 3, that's 10. And finally, and apologies for anyone who's red-green colorblind, I'll try to, this will look the same to you, I apologize. It's the second row times the second column. 1 times 1 is 1, 2 times 1 is 2, 3 times 1 is 3, so it's 1 plus 2 plus 3, which is also 6. And there we go. So we've actually changed, so we create a product matrix that is different from the dimensions of either of the two constituent matrices. That's what we get. Okay, and that's matrix multiplication. And there's examples in the problem sections and the problem sets to work through, but that's all there is to it. You have to just keep track of all the different rows and columns and make sure you take the dot product of the appropriate row with the appropriate column. That's that. Now I said there's one more kind of multiplication. Now at this point you might be thinking, yeah, but there's only one more kind of multiplication that we're going to deal with here. That's called a Kronecker product. And this is the kind of, this you see much less frequently, although it does occur in some panel-corrected standard error models, but it's a less frequent thing you see. It has a different notation as well. If you have a Kronecker product between A and B, it has that notation. If that's C, the way you do this is by basically sticking B into A. So this is how it works. Let's say A is some 2 by 2 thing. 1, 2, it's a 2, A2, 1, A2, 2. Let's say B were also 2 by 2s to make all this a little easier. B1, 1, B1, 2, that's a B. B2, 1, B2, 2. Oh, A, Kronecker product, B, that's not really a verb, is going to be this much bigger 4 by 4 matrix that consists of A1, 1, B1, 1, A1, 1, B1, 2, A1, 1, B2, 1, A1, 1, B2, 2. The same thing on here with A2, 1, and the same thing over here with A1, 2, and the same thing over here with A2, 2. So in other words, it's the matrix A, like this, A11, B, A12, B, so it's a block matrix, in which you scalar multiply the components of A times the entire matrix B, and each one of those scalar multiplications ends up being a block of the bigger matrix. If A is n by m, and B is p by q, then C is going to be n times p by m times q. So it's a much bigger matrix in theory. And you see these semi-often, well, not really much often at all, in stuff like panic standard errors in some models, but just for completeness, there you go. And that covers matrix multiplication. In the next module, we'll deal with some less familiar, not this is familiar, but less familiar operations than multiplication, like the trace and the determinant. Thank you very much.